Today's lesson and objective was really about getting the kids to talk about some tasks that we put forth to them. And our goal really was just to see what they came up with. So part of my deal today was I was listening and walking around and trying to think about how I can enhance the lesson by questioning strategies, but letting them work through the problem first. So at the beginning of class, I focused on the warm-up to get them going. Originally, I had them start and just look at the problem and see if they can make sense of the problem and decide what direction they wanted to go in. After a few minutes, I chose to then have them talk in A-B partners to see kind of if their neighbor had the same strategy they did. And then I followed that up by going to a 4 group and letting them discuss it together and come up with the best plan that their group wanted to present. After that, I went into a performance task, which allowed the kids to keep that group momentum going, and questions that I posed in the warm-ups were kind of a lead-in to get them to think of those things while they were also doing the performance task. It was something that I wanted the kids to explore, and I thought it was meaningful when I hear the kids say something that I go from there and kind of change my instruction, or at least change the way I directed where I wanted them to go with that. For all of my group work that I ever do, whether it's A and B partners or 4 groups, I spend a lot of time in my seating chart. So I'm very specific on who sits where and why they sit there. For example, in a 4 group, after each assessment I give for a chapter or a module, I'll re-rank all the kids in the class on their strengths and their weaknesses. And then I'll actually put them into like specific groups. For example, if there's 9 groups, the top 9 kids would be like the 9 captains. And how they select people in their group is just based upon who's available when it's left. So when they get into their groups, they'll have the strengths separated out, and how they're able to communicate, it doesn't really intimidate any of the kids. So each kid in every group feels that their group is strong, they feel balanced, and I feel like even in this scenario, even the weakest kid in the group has an opportunity to speak. And the way we set it up is everybody has an opportunity to speak, and their roles are very important. We've had a lot of success at this school with that setup, and so I continued to use that today, and I think the result was great. When I'm setting up my lesson, I look at the standards for mathematical practices. One of the ones that I think that encompasses all of them are standards for mathematical practice number 1, which is make sense of every problem and persevere through solving them. And standards for mathematical practice number 6, which is attend to precision. Which again, I try to have that kids focus not on just their calculations, but how they communicate what they did and what they saw in the problem. So today during the warm-ups, our focus is just getting kids to start. I would say even 5 years ago, prior to starting the PLC training through Math Generation, it was a standard. I take 5 problems from the night before, I put them up on the board, and the kids are super quiet, and then I ask somebody for the answer, and I say, you are correct, and then I just move on. So I believe in the last 2 years since shifting towards some of the standards for mathematical practice, and then being part of the PLC training that's offered through Math Generation, I've really enhanced the start of my lesson. And so we pose either a question or a specific math problem. So I walk around the room and I'm really looking to see how many different ways the kids started the problem. And even halfway through, I might call out and say, interesting enough, there were 3 different ways people started this problem. And I might even be humble and say, I only thought of 2. And then I give them a chance to work through the problem a little bit more. They might even have an opportunity to work with their A and B partner, or even their group partner, prior to them debriefing the problem together and then maybe coming up and presenting it. When you start on your warm-up today, what I'd like you guys to do is, I would like you guys to just take about 3 minutes, all right, to look over, try to make sense of the problem before you start coming up with some ideas of what you want to do. We're going to go 3-minute individual, then we're going to go to a 3-minute AB, and then we're going to go to a 4 to 5 minute all group. And I'm going to walk around and select some of you to come up and debrief that particular problem and present it in front of the class. Standard stuff. And then we'll go move right into a performance task that I'm looking forward to seeing what you guys come up with. Okay. So are there any questions for me at this time so far? Okay. That's interesting. Why did you naturally draw that parabola down? How'd you know to draw that parabola as a down U?
The ball would hit the ground, come back and down and hit the ground.
Okay. If you're looking at the formula in standard form, did anything else tell you?
Not really.
No, not really? Okay. What do you think the quantities are here?
It's the y-axis, so like the height.
So it'd be the height. So you're talking about the height of the ball?
Yeah.
Okay. And so what would be your quantities on the x-axis?
The time.
Time. All right. Like it? Look up really quick. I know you're not done with the problem. That was not the intention. I just wanted you to kind of get a feel for the problem. So for the next 3 to 4 minutes, I want you to share with your A and B partner how you started the problem, because everybody actually started. And I want you to share how you started the problem and what your thinking was and how you started the problem. Okay? So right now, within your A-B partners, go ahead and kind of share what you guys did.
The highest thing, and so then you plug in for negative 2 to get 2, and that would be your x-axis point for time.
All right, look up one more time, you guys. I want to find out a couple things. Please raise your hand if you and your partner had a different starting point of how you thought about the problem, because I saw a couple on there. Okay? All right? Anton, how is your guys' different?
I started it by trying to plug numbers into the equation. He was graphing the points.
Okay. So when you say you were plugging numbers in the equation, well, let me ask you guys. When Anton said he was plugging numbers in the equation, what do you think he was looking for? What do you think he was looking for? How many of you guys started substituting numbers in? I saw a bunch, right? About a third of you. So what were you thinking? What were you looking for?
The roots.
So you were looking for the roots. So where it might, what would the root tell you? Chan?
Where it intersects the x-axis.
Ah, where it intersects the x-axis. Now, in this particular problem, what does that mean? Right now, actually take 30 seconds to discuss with your A and B partner what you think the intersection of the x-axis in this problem means. All right, go.
So when it hits the x-axis, that's how we know when it hits the ground, and we can find out the time when it hits.
Yes, so well, we know it can't be negative 1, so there's only one possible ending point, which is 5 seconds.
So there's only one root.
So the roots basically mean that
When the ball hits the ground after starting its initial point.
but I was thinking,
And there's only one root because it starts on the y-axis.
and you get like 3.
Let's transition back up. So I gave you a few seconds to discuss what you thought that intersection of the x-axis mean. I keep hearing people say that as I walk by. So somebody needs to debrief and tell me what you think that means. Seth?
The point at which the height in this problem is at 0.
At 0. Okay, so what is this problem again? We need to kind of go back to what the original problem was. It was a ball being thrown up in the air. So you're saying as it hits the ground then, that's going to be one of the roots. Okay, all right. And what do you think the other root is then? Think about what the other root might be. How many of you factored it? How many of you factored it? Okay. What happened when you factored it? What were your two roots?
5 and negative 1.
5 and negative 1. Do you think any of those are extraneous? They don't work?
Yeah.
Which one? Negative 1? Why? Why does negative 1 not work?
You can't have negative times.
You can't have negative time. So you're saying that it's possible for you to solve a problem algebraically and have two answers, but one of them just not make sense. All right? Here's a big question that we have never discussed before. In your 4 groups, I want you to talk about why you think it is going to be a negative root. Why it became a negative root other than factoring in the actual problem of a ball being thrown up in the air from, what was that, 25 meters starting height? And as they threw it up in the air and it came down at whatever, what was the time again? What was the time that it hit the ground?
5 seconds.
5 seconds. Why did they get a negative 1? Why do you get a negative 1 when you factored? Why did that happen, right? Spend about 60 seconds talking about that.
The original starting point was actually 0.5 feet above the x-axis. It should be, like, we can tell that if it started here, that would be the original root, but since it didn't.
It started up there, yeah.
Yeah.
And then it would hit over here.
And you can't have a negative time either.
No.
So technically there's only one root.
Yeah.
No, there.
But there's two.
Yeah,
roots,
there's
so
one
doesn't
is
work.
irrelevant.
Yeah.
Yeah.
Doesn't work.
So starting heights here, you knew one of the roots was going to be negative. That's pretty good. I like that.
Oh, so H is the highest point in the front. C would be the initial starting point, which was 25.
One of the things that I think that the kids have enjoyed more than I anticipated was the amount they like to share. And when they're feeling confident about how they communicate what they know, they're really doing a good job coming up. A great example would be at the end of the year, kids kind of write letters to teachers. And one student said, I really want to thank you for giving me an opportunity to be in front of a classroom. I am very shy, as you know, and I feel this has helped me come out of my shell. And it's in something that I'm strong at, mathematics. And I was not strong at communicating, and I feel just in the 10 times I came up last term, it's made me a more confident person. So I heard some really good things, so I need you to share. There were two really good explanations that I heard. I know there were more, but I need somebody to kind of share out how they kind of knew where one of them was going to be negative. All right, one of the roots was going to be negative, and why it doesn't really make sense in the problem. And about 5 other people had the exact same thing.
So, because I knew that it started at 0.25, it didn't start on the x-axis where the root was 0, so I knew it had to go down here to the negative.
Now, that axis of symmetry, where's that going to be? Where's the axis of symmetry going to be? S-man?
It's going to be the maximum height.
It's going to be right at that maximum height, all right? And how did some of you, I see a 2 there, how did some of you get that 2? Juwan?
Negative b over 2a.
Oh, so you used the rule, x equals negative b over 2a. And what else does that give us? That gives us the axis of symmetry, and what else? What else?
The point on the x-axis where it will meet the maximum height.
Right, so the x-coordinate of the vertex then. Okay, so here's what I'd like to do. I only want to spend a few more minutes in 4 groups, and then I actually want 2 groups to come up and present 2 different ways of doing it. I'm assuming the one that I saw half of you do was factoring, and the other half of you went and substituted some numbers in, and you actually created the parabola just like you see here. So we're going to see some of the same things, but I want to see how you debrief it.
I'll say it again. So you had this equation right here, and I plugged in different x values to get the y value. And so first when you started off at 25, you already knew that it was 0. And then when you threw it up, I plugged in that x is 1, and the y value ended up being 40. And then when I plugged in 2, it ended up being 45. And so when I plugged in 3, it ended up becoming 40 again, so I saw that it was coming back down. So the maximum had to be 45, and that was a line of symmetry. And then when you plugged in 4 as the x value, you got 25 as your y value. And it showed that it was coming back down, and that's where it started as the same height. And when you plugged in a 5, you ended up getting 0. And when you saw that, it showed that this 5 value as x was a root, because that's where it intersected the x-axis.
And how did you know that it was 2 seconds again? Negative b over 2a. All right, so you did it from standard form then?
Yeah.
Where'd you get that negative 20 from? Is that the upper velocity of v sub 0?
Yeah.
Okay, all right, just wanted to make sure. So you're just in standard form right now?
Uh-huh.
Okay.
And so the ball was 2.
Oh, okay. I see.
But
That's just the regular formula for a ball thrown.
yeah, but then you just plug in numbers.
Yeah. So that's that's how a clarifying question works.
Okay.
We understood how that related.
I think that
So I definitely
would be a good one, construct viable arguments, because when we all got into groups, we had to.
You gotta, yeah. So
Yeah.
definitely three.
So number 3.
How about 2?
I think 2.
2 also.
2.
Yeah, because you have to reason abstractly.
And then
I think that's good.
4 is model of
Model with
mathematics.
We didn't really
mathematics.
model.
Well,
Yeah.
we used a graph.
Well, we applied
We
it
did.
in everyday life.
and we used a graph.
Yeah, because it is a word problem. So
It's a word problem. So 4
I
also.
think that's all that
And
applied.
then what's on the back?
yeah,
So we're just
Well,
missing
there's
5.
6.
We're missing 5.
we didn't use any tools.
We didn't use tools, so no 7 or 8.
Structure, no.
Look for no.
So I think that's all
so
that
I think
applied.
So 1, 6, 3, 2, 4. So
Yeah.
You guys make sure you have it all structured. I'm going to have you guys do some of the presenting, so you guys kind of talk about that. Okay?
Okay.
I saw somebody graph the -1 and the 5 and then just draw the line of symmetry. You don't even have to, if you factor right, now that you know a lot about it, you don't even have to use -b/2 if you don't want to, because you know it's going to be in between, right? The line of symmetry. So that's good stuff, you guys. Really good stuff. Okay. Did anybody factor out a -5 first?
Yeah, I did.
Oh, you did? You factor out a -5 first, okay. Okay, good, good. I like that. Really good stuff, you guys.
You know, have that -5, you know that it's going to be a down U. So without that, I mean, I think it kind of changes how you would theoretically graph the equation.
Some of you were you did a great job talking about extension questions. I just heard one about the ball bouncing, and we're going to get into that here in a little bit. This will be a long warm-up for you because some of the things I heard you guys say, really amazing, and I want to talk about that a little bit further. So let's get 2 minutes to wrap it up. We're going to get a couple groups up there to debrief, and then I really want you to focus on beyond this problem, or how do we extend the problem, okay? All right, 2 minutes.
Maybe if you're playing golf, because golf is pretty slow. No, because this time there's like a starting height though, not just
True. Maybe if you're on like a hill on a golf course and you gotta shoot it into the.
Yes.
Okay.
So we're gonna have a couple groups present, and remember, we want to critique the reasoning of others. How was theirs the same as yours? How was it different? Look at some of the similarities of what they did and what you did, and look at some of the differences. I heard one group over here say, we could have did that from the beginning. And I heard a group over here say, wonder what would happen if you graphed the ball bouncing, what type of ball it would be. And we'll talk about that when we get to some extension questions, because I think those will be very valuable to you understanding and really putting meaning to the problem.
All right. So for A, the question was, when will the ball hit the ground? And so what I started off doing was I saw the equation, or the equation, and then I perceived time to be x and the height to be y. And so I plugged in different x's to find different y's. And I found out that y would be 0 when x is 5. So I got the ball hit the ground at 5 seconds. And for B, we had to find the when it would reach the maximum height. And so I looked on my graph, and the point was highest at 2 seconds. And that happened to be when it was 45 meters up.
So it's 45 meters up. Okay. Let me ask you a quick question. At that point, you guys, did he use a formula? Did he factor? What did he do that was a little bit different than the way some of you did it? I just saw something there on D. What is that 1, 2, 3, 4, and 6? What are those? SMP. Oh, so you felt like, let's see, you definitely did SMP 1, right? And what else do I always say you're doing for the last 2 years? 6, 1 and 6, attended precision. And I think he was pretty precise on the way he described that. And you thought 2 was reason abstractly and quantitatively? I would say he had to do that, right? He didn't start plugging in negative numbers. Why did he not plug in negative numbers? Time's not going to be negative. All right, very good. And then for modeling, you think just by graphing the problem, he modeled it? I would say that also because it's a word problem and they're asking for a specific set of values that they want to know. All right. And again, like I said, my favorite is always 6, making sure you're precise. All right, thank you very much. Good job, Daniel. Throughout a lesson, I think it's extremely important that we don't give generic compliments. So when I give compliments to students, it isn't great job, kids. It's I like the way Billy set this problem up. He was very precise when he modeled the problem. So what I've found that, and the kids appreciate more, is it's specific to either them, their group, and even the class. You can be specific about how they transitioned into something or how they enhanced the problem and how they're thinking. So one of the goals for me as a teacher the last 2 years is I've been really focusing on how I give praise and that it's meaningful and it's less generic than just saying great job, kids. They've been hearing that forever. They leave the dentist's office and they get a sticker, and I just never wanted to be like that. I want to know that they specifically did something great, and so I try my best to do as many of those compliments but make it really meaningful and direct to what I saw, whether it's how they communicated, how they set up a problem, how they communicated in their group, a leadership role they took, or just how they found a mistake I may have made in a problem.
Find the vertical
So the first question is asking the vertical height of the bowl of glass 3.
So let's draw the triangle
of glass 3. Be precise, be clear, be concise. Be clear, and if you're going to be clear, be crystal clear.
Yeah. Oh, okay. I know that. Okay, so let's just solve for the volume of the sphere, and then we can divide by 2 after.
Where are you guys splitting it at?
So you split it in half.
Yeah, I can divide by half.
So right here, did you guys do a...
We use the Pythagorean theorem.
Oh, Pythagorean theorem, okay. Yeah. And so, and that 3 then comes from...
Half of 6.
Okay,
6, yeah,
I like it. Now, how did you deal with that that hemisphere?
It's a half circle, so we found
so we found the volume of the sphere,
and then
sphere.
Not circle, sphere.
Sphere, and then you just cut it in half.
Divided it by 2. Yeah, by 2.
No, you just said 4, 6. That means you just manipulated the formula.
Yeah.
So to include, yes. So you actually made your own formula for a hemisphere.
Yeah.
Okay, 4, 6, or 2/3, right?
Yeah.
All right. Yeah, think about that, right? Huh? That's why they pay me the big bucks, boys.
Yeah, but you know what I'm saying is, the radius could be, this could be 3, or this could be 3. It's either way. But if you look at a circle, what's basically a sphere?
Yeah, it goes all the way around.
Yeah, it's the same thing. As long as it's from the center to the edge, it's a radius.
It's the top, only the bottom half of it is a sphere, so the top half is a cylinder. So if we extended it more, it's like, let's say you were making the radius like 4 from here, like from here to here, then this part wouldn't be a sphere because it's like already part of the cylinder.
So your volume is this.
Get it? So like it would be a pill shape, I guess.
Okay.
So.
All right, everybody look up, please. I love some of the critiquing you guys were doing on number 3 and the challenge that it has, and I'm looking forward to some people debriefing it and critiquing it.
Number 1 is said find the vertical height of the bowl of glass 3 and show your work. So the glass 3 is a cone up here, so it has a diameter of 6 or a radius of 3 and a slant height of 6. So I cut that in half to get this right triangle, which has a small length of 3 and a hypotenuse of 6. So we're trying to find the height there. So what you do is, since the smaller leg is actually 1/2 of the hypotenuse, you can use the converse of the 30, 60, 90 theorem, which is the longer leg is √3 times the length of the shorter leg, so then it is 3√3 is equal to the height, and then I got the height is approximately 5.20 centimeters.
So how do you think almost everybody else at this school would have done that particular problem, including you and me, right? Clovis? Pythagorean theorem. Did anybody else see the 30, 60, 90? Santiago, I take back everything I said about you, man. That is really good. 30, 60, 90, pretty impressive. Do you see it now? Where the hypotenuse is twice the length of one of the legs. So then with the ratios, it's going to be 3√3. Yeah. Wow. I'm not that embarrassed. I mean, he's a smart kid. I didn't see that. So very nicely done. As we're shifting towards some Common Core math standards and the mathematical practices, the other thing that has become more aware to me is how to differentiate my instruction. Prior to 2 years ago, to me, I didn't really know what it meant. I've been to workshops, I've been to speakers, and I still never got a clear view of what it is. And now I feel much more comfortable about in the classroom how I can differentiate instruction. And to me, it comes from the questions that you ask kids. We can ask different types of questions to the same problem and have some of the same goals in mind. So I might ask student A a specific question about a quadratic equation. How do you know that it opens upward as a graph? But I might ask student 4, why would this have 2 roots? And what does it mean to have the roots? So I believe now with these mathematical practices, student standards for mathematical practices, and the standards getting more in depth, I have a better grasp of differentiating within the class, within the same problem, and the same problem sets that I hand out. I feel as a teacher, at first it was such a scary idea to have this huge shift towards the standards for mathematical practices and the new Common Core content standards, but I feel like a brand new teacher. I'm excited about the possibility of getting kids to think deeper and to understand math more than that one day you taught a skill. So I definitely am excited about this opportunity, and I take the fear and put it into the excitement and into the planning and work with my colleagues to come up with better problems and better questioning strategies. And we're just excited about our work, and we're excited about the years to come.